I had Rootman still wrong. My goodness me. R-U-T-M-A-N. Krein Rootman. Okay, so we were talking about Fredholm alternatives. We saw the finite rank Fredholm alternative for finite rank operators, and then we moved it up to compact operators. And now we want to use it to look at the spectrum again, at the spectrum of compact operators. So it is the spectral Fredholm alternative. So A is a compact linear map in a Hilbert space. Then sigma of A is compact, and the only possible limit point is lambda is equal to 0. Furthermore, each lambda which is non-zero is either in the resolvent set or in the point spectrum. If it's in the point spectrum, then the eigenvalue has finite multiplicity. So you see, this is a rather strong result, right? We don't have to worry about the continuous spectrum or the residual spectrum. And in the point spectrum, we only have to worry about finite multiplicity. The proof will be rather simple, just using the previous one, the compact Fredholm alternative, for the set G to be C without 0, and the operator B lambda to be 1 over lambda A. And then we can directly apply the previous result and get the alternative as listed here. Notice that 1 over lambda to infinity is possible, which means lambda goes to 0 is a possible limit point. And then here is the Hilbert-Schmidt result, which I have shown you earlier already. So now A is a linear compact self-adjoint operator. Then it has a spectral representation. A phi is a sum I is 1 to infinity, lambda I, phi, psi, psi, where psi is an orthonormal set of eigenfunctions. Let's prove this. So since A is self-adjoint, we know that all eigenvalues are real, as is here. And then we know the eigenvalues from a discrete set with finite multiplicity. So we can enumerate them according to their multiplicity, and also enumerate the eigenvectors, which then form an orthonormal basis. So then we set M to be the span of all those psi. First we show that the range of A is in M. So A is mapping inside M. Since A is compact, we have AM is equal to M, because the psi's are all eigenfunctions. But now let's look at the orthogonal complement. So for phi in the complement M orthogonal, we have A phi psi is phi A psi, but this is 0, because the psi's is a span of the psi. This is all in M. And we used A as self-adjoint. So, meaning A phi is in the M orthogonal as well. And this means that both M and M orthogonal are invariant under A. So now we define A hat to be the operator A restricted to the orthogonal complement. And of course I want to show that A is 0. First of all, A is also self-adjoint because it is A hat is self-adjoint because it is A restricted. It's also compact, and each spectral value is an eigenvalue. So we are looking at the eigenvalues of A hat. But then if A hat would have eigenvalues, then the eigenvectors belong to M. And it would not be an M orthogonal. So the spectrum of this operator must be empty. And this implies that the operator is 0, because if it's non-zero, we have a non-empty spectrum. So this means that we can express AU in the eigenbasis as written down here. So this means that the psi is really a basis of range A, meaning that each A of U can be represented in a spectral representation using the sum of the psi with some coefficients. Okay, so this is how far I want to carry the spectral theory. Let us just quickly summarize what we have learned here. Right, we are talking of linear operators between Banach spaces. The spectrum has 3 parts: the point spectrum, which is eigenvalues. The continuous spectrum, this is where the resolvent exists with a dense domain, but it is unbounded. And then the residual spectrum, where R lambda A exists, but the domain is not dense. Then a useful tool has been the Newman series for I minus A inverse, which is the sum k is 0 to infinity a to the k. We needed a is less than 1, otherwise the series would not converge. The spectral radius is given as a supremum of the absolute value of the lambda, and this is bounded by a if a is bounded. The resolvent set rho is C without sigma, and this set is open. Now here I also summarize the spectral theorems. So if A is symmetric in a Hilbert space, then the point spectrum and the continuous spectrum are real, and eigenvectors, if we have any, are orthogonal to each other. A compact operator on a Hilbert space, then the spectrum equals the point spectrum, and lambda has finite multiplicity, and there might be an accumulation point at 0. If A is compact and self-adjoint, then we have items 1 and 2, and the orthogonal representation of A.